Okay, let's spend some time. We're going to continue talking about asymptotes. There are actually going to be three kinds of asymptotes. We've already talked a little bit about vertical asymptotes. We did mention about horizontal asymptotes when we were looking at graphing. And there's one more called oblique asymptotes. So as a quick review, usually these different asymptotes come about when you have what we call rational expressions, which are like expressions where you have like a fraction with variables in the top and the bottom. Now we earlier talked about how to find vertical asymptotes. And vertical asymptotes, you basically look at variables in the denominator of your fraction. It's not very hard. Vertical asymptotes is just a matter of you look at the variable and you say what values of x would cause that denominator to equal 0, and those become your vertical asymptotes. So for this example I just wrote up here, vertical asymptote would occur when x is -2. Or if we were to try and graph I can right away draw in my asymptote. And that would help me if I tried to graph this thing. Vertical asymptotes, all right, not too bad. Let's talk about horizontal asymptotes. Now actually, we're going to use a principle that I talked about a video or two ago. Now it's going to come, and I told you we were going to use it again. And that's the idea of end behavior. So let's just do some examples. So say I have this was my rational expression, and they asked me to find the asymptotes. First of all, what would the vertical asymptotes be? Well, if I factor this, it would be x plus 3 times x minus 3. So I have vertical asymptotes at x equals 3 and x equals -3. All right, that's pretty straightforward. Now what about horizontal asymptotes? To determine horizontal asymptotes, you use end behavior. Remember what I talked about? End behavior is what happens to your expression when x gets really big, either a huge positive number or a huge negative number. And remember I said end behavior means everything else goes away besides what we call the leading term, the term with the largest exponent on the variable. So if I look at this, at the numerator, x squared minus 2x plus 1, it's like I can sort of ignore the 1, I can ignore the 2x because they get dominated by the x squared. When I look at end behavior, when the x gets really, really big, the x squared dominates. These other terms become insignificant. And if I look at the bottom, the 9 goes away and becomes insignificant compared to the x squared. So as I think about end behavior, and that's what asymptotes are concerned with what happens at the edges of your graph when x gets really big or really small. In a sense, I'm left with approximately, in this case, x squared over x squared. Now let me just say, as we're looking at horizontal asymptotes, there are three scenarios that can occur. And this is the first scenario. Now the first scenario I'm going to call is when I first look at my original function, I notice for the leading terms that the exponents are equal, top and bottom. So here is the first thing that can happen. You're given a rational expression. You look at the leading terms. The exponents are the same. When you get rid of everything else, what happens? X squared over x squared, those cancel. If those cancel, you're left with just number 1. You know what this says? This becomes my horizontal asymptote, because f of x is the same thing as y. So what's interesting is we can actually do some interesting stuff based upon just asymptotes. First of all, I said the vertical asymptote should be 3 and -3. I can draw those in. And then based upon this, once again, when I reduced and only kept my leading terms, and then I compared those, because they had the same variable, they canceled out, it's like I would actually have a horizontal asymptote of 1. So if I were to actually try and graph this thing, it would be, I would have like maybe 3 different pieces to this graph. Something in the middle, something on the right, something on the left. You can end up with some pretty funky looking graphs. Let me do another quick example of when the exponents are equal. How about if I had here's a rational expression. I'm going to find the horizontal asymptote. I only keep the leading terms, which ends up being 3x squared over x squared. The x squareds cancel out. But in this case, up here I was left with 1, but here I have 3 over 1. So then here, my horizontal asymptote would actually be y equals 3. If I were to try and graph this at some point, I'd go to y equals 3, and there's my horizontal asymptote. So the key is, when the top and the bottom of those exponents are equal, you know what ends up being the horizontal asymptote? It's really like it's the ratio of these coefficients. There's really a 1 here. If you look up here, what's the ratio of the coefficients? 1 over 1, which is 1. 3 over 1, which is 3. Not too hard. So I said 3 things can happen, and here's what they are. Here, the leading terms equal exponents. The 2 other things are when the leading terms, when either the top is bigger than the bottom or the bottom bigger than the top. So let's just see what happens in those situations. So you have a rational expression. We're going to try and find the horizontal asymptotes. And here we have, we'll say the top is bigger than the bottom. Let's do this. Let's do bottom bigger than the top to start with. Bottom larger than the top. So for instance, so here's a rational expression. Once again, for horizontal asymptotes, all I care about is the leading terms. I get rid of those. So I'm left with approximately 2x over x squared. Now if I cancel here, I got an x on the top, x squared on the bottom. When I cancel, I'm left with 2 over x. Now horizontal asymptotes, we're trying to figure out what happens when x gets to be a really, really huge either positive or negative number. So if I ask you, okay, let's grab your calculator and let's put in 1,000,000 for x, and let's see what this equals. What is 2 over 1,000,000? I don't know. like 0.000002. I don't know. One thing I do know, it's a very small number. Matter of fact, it's so small, basically I say it's almost like nothing. It's almost zero. I mean, it never actually gets to zero, but it gets to be so small. It's just almost like nothing. So that's what you say. Basically, when the bottom is less than the top, when these things cancel out, because you're left with a variable in the bottom and just a number in the top, basically, it's going to end up equal to 0, which means my horizontal asymptote, in this case, is always going to be y equals 0. It's always 0. So if I was going to try and graph this, I could start out by saying, you know what? Here's a horizontal asymptote. All right, so quick review. Rational expression, horizontal asymptotes. Top and the bottom are the same. Exponents are the same. It's like the ratio. The variables sort of cancel out. However, here's a case where if the bottom is larger than the top, then we're left with a variable in the bottom, and because of that, the whole thing goes to 0. We always have horizontal asymptote of y equals 0. So now the last scenario is when the top is larger than the bottom. So what happens here? Once again, we always only look at the leading terms. I don't care about anything else. So here you can see the top exponent's larger than the bottom. By the time I cancel out, in this case I'm left with x over 2. Now let's think. So what happens, we're looking at in behavior, what happens when this x gets to be a huge positive or negative number? What happens to this number? Like, if x equals 1,000,000, what would this thing be equal to? Well, 500,000, right? Half of a million. If x is 1,000,000,000,000, what happens? It's like 500 billion. So what's going on? What happens as x gets huge? You know what? As x gets huge, this whole number gets huge. It just keeps getting bigger and bigger and bigger. Well, the idea of an asymptote is where the number approaches the same number. In other words, maybe I didn't make this clear. If we were to have a graph like this, we would have maybe some kind of graph looks like this. The asymptote is what the graph begins to track and begins to approach and get close to. Maybe for this one, maybe it would look like this. For this one, maybe it looks like, who knows? Maybe it looks like that. But you know what happens in this case? If I were to graph this, you know what my graph does? It just gets bigger and bigger. It doesn't approach anything. It just keeps getting bigger and bigger and bigger. So what happens is when the top is bigger than the bottom, there's no horizontal asymptote. Actually, this would probably be like a straight line. No horizontal asymptote. So the three scenarios, when you're looking at horizontal asymptotes of rational expressions, if the leading terms, the top and bottom, are equal, it's going to be the ratio of the coefficients of the leading term if the bottom is bigger than the top, you're always going to have a horizontal asymptote as y equals 0. And if the top is bigger than the bottom, no horizontal asymptote. But now, there's one certain special case of number 3. Sometimes with number 3 can lead to a thing called an oblique asymptote. And this happens for a special case of number 3 where the top is only one, the exponent is one number higher than the bottom. What do I mean? Say you have say we had this. So we notice the top is bigger than the bottom, so we know right away there's no horizontal asymptote. Because once again, all we care about is the leading terms. But then, because my leading term is x squared here, and my leading term is x here, so the top is just one larger than the bottom. In this case, I end up having something that they like us to look at called the oblique asymptote. So let me just show you how to figure out the oblique asymptote, and then let me sort of explain what it actually is. So how do we find the oblique asymptote? Let me write down the function we were just looking at. So it was this, x squared plus x minus 1 over 2x minus 2. To find, so I know it's going to have an oblique asymptote because the leading term is x squared, the leading term in the bottom is x. It's one bigger. I have to figure out this oblique asymptote. What do? Amazingly enough, we're going to do old-fashioned long division. We're going to take this fraction and turn it into a division problem. So really, we could think of this as x squared plus x minus 1 divided by 2x minus 2. We're doing like old-fashioned division, except we got some variables and stuff instead of just numbers. Hopefully you remember how to do old-fashioned division. In this case, you look at this leading term here and this leading term here, and you say, I'm going to put something here. What times 2x would equal x squared? Hopefully you can see 1/2 x times 2x. So you get x times x, x squared. 1/2 times 2 is 1. Now what I do is I go ahead and multiply this out. I multiply 1/2 x times 2x, which is x squared, and 1/2 x times negative 2, which is negative x. And remember division, then what you do is you subtract that. X squared minus x squared is 0. X minus a negative x, x plus x, it's like 2x. I bring this next term down, and I go back up here and I say, what times 2x would equal 2x? And I say, well, 2. So I put a plus 2 here, so 2 times 2, 1. 1 times 2x is 2x. 1 times negative 2 is negative 2. Now I subtract this. 2x minus 2x is 0. Negative 1 minus the negative 2 is plus 1. So that becomes my remainder. So you know what I can say? This thing equals, I take this right here, 1/2 x plus 1, and then plus my remainder, 1 over. Now if you haven't done long division in a long time, and especially long division with these polynomials, then you might need to get some help with it, but this is what happens. Now, once again, end behavior is what goes on when x becomes a really large number. Now, this last term, since I have an x in the bottom, when x gets really huge, this whole thing basically approaches 0. So when that happens, once again, I'm left with approximately this for my asymptote. Now I've got a variable here, but if you remember, this kind of equation is a straight line. It's an asymptote, but it's a straight line, but it's not vertical or horizontal. It's actually at an angle. And I can actually go and I can plot this asymptote. It's at an angle. If you remember how we graph lines, if you remember y equals mx plus b, b is like my y-intercept. 1/2 is like my slope. So up 1 over 2. What I do is y equals 1/2 x plus 1 becomes what I call my oblique asymptote. And I graph that as a dashed line. And if you were to finish the graph, it might look like something like this. Once again, because what happens, an asymptote is where the graph begins to get next to and begins to track the asymptote, but never actually touches it. These other examples, for horizontal asymptote, my graph becomes sort of horizontal. Or for a vertical asymptote, like this, begins to go down. But here's the case where my asymptote is actually at an angle, and so it begins to go up like this. Wow. All right, that was a lot of stuff. So now I'm actually going to look at, the easiest thing is now, I have some example kinds of problems, sort of like homework problems. I think the easiest thing I've decided is to try and look at some of these and see if we can answer the questions based upon everything we've done so far. So for instance, let's just go and do these and maybe we can finish out this last video. So here's a problem. Looks just like something you'll see in the homework or the quiz. I may have to zoom this in so you can maybe see it. So here it is. They give you this function. They actually call it r of x. Maybe r stands for rational. 9x plus 9 over 4x plus 8. And then they ask you a whole series of questions. So let's just work through this and see if we can answer these questions based upon everything we've talked about. What is the domain of r of x? The domain of this. All right, so let's review domain. Remember domain? We're going to assume it's all real, except we have to look at the denominator and say what value of x would cause the denominator to be 0. What I'm going to do is I'm going to go and factor the denominator. I can factor out an x. Now when you look at it now, what value of x would cause the denominator to be 0? Well, I know x cannot equal -2. Now this actually is a multiple choice question. So here's that set notation. So I know here it says x can't be -2. Here it says x cannot be 0 or -2 or -1. Basically, That's the correct answer. The domain is all real except x cannot equal -2. Then they say, part B, what is the equation of the vertical asymptote? Well, the vertical asymptote comes from whatever value of x would cause the denominator to be 0. Now in this case, they write it like the equation of a line. So up here I'm saying x cannot equal -2, but when I draw the line, I basically say it's the vertical line, x equals -2. So if I were to eventually graph this thing, I would have that. And I think eventually we are going to graph it. C, what is the equation of the horizontal or oblique asymptote? So now it's talking about horizontal or oblique. So now it's talking about looking at leading terms and what goes on. Now here's the thing I didn't mention. Here I factored, but when you want to look at horizontal asymptotes, you need to look at the unfactored equation. Matter of fact, if they give you an equation that's factored, you have to multiply it out because you want to look at the unfactored rational expression. Because what's going to happen is, if I look at the leading terms, first of all, what do I look at? My leading term, they're the same. Exponent on the top, exponent at the bottom the same. Therefore, what happens? It just becomes a ratio of the two coefficients. So basically, y equals 9/4. And if I were to draw this, 9/4 is 2 1/4. So 1, 2, maybe I would have horizontal asymptote like that. There is no oblique asymptote because the oblique asymptote only occurs when the top is one more than the bottom. But we do have a horizontal asymptote. Now the last step is they sort of want you to figure out then what the graph of this is going to be based upon what we've learned. So first of all, it's multiple choice, so let's try to eliminate which ones we know are not true. So I've already initially done some of this, so I know I have to have a vertical asymptote of -2. Look at the vertical asymptote here. It's over here at like +2. I know that's wrong. I know I need to have a vertical asymptote at -2 and a horizontal asymptote at this 2 1/4. So this looks like a this one could be correct. This one could be correct. This one, once again, the vertical asymptote's not. So by process of elimination, I'm already down to B or C. Now I just have to figure out, and actually, we'll look at my horizontal asymptote. I know it's up here at 2. This one is down here. Just by process of elimination, I've determined that should be the graph. And just so I don't cause problems, let me look at that actual answer so I don't make a mistake on this video, then have to fix it later on. So let me see. A is A, B is A, 9/4, and B. Yep, those are all correct. All right, let's do a couple more of these. Hang on a second, let me find the ones I want to do. Let's do this one. Seven over x squared minus 9. What's the domain? Once again, the domain, all I care about is the denominator. Once again, I'm going to need to factor. What values of x would cause the denominator to be 0? It looks like 3 and -3. So here are my choices. I know the domain is all real except 3 and negative 3. Looks like B. Vertical asymptotes. All right. Whatever values of x would cause the number to be 0. So it looks like it's going to be x equals 3 and x equals negative 3. So I think there's actually 2 vertical asymptotes, 3 and negative 3. Horizontal or oblique. So what do we have here when we compare leading terms? We have 7 and we have x squared. So there's a case where the top is less than the bottom. And we said for that case, it's always y equals 0. So there's no oblique asymptote. So now, based upon what we've learned so far, before we figure out the graph, what would we say? I got vertical asymptotes, negative 3 and 3, horizontal at 0. So let's look at our possibilities. First, this cannot be correct. I only have one vertical asymptote. Now this one looks possible. I got the verticals and it looks like a horizontal because I can tell the graphs. That's a possibility. This one looks like a possibility. This one, only one. So it goes on between these two. So let's do this. I just have to pick some place on this graph and compare my equation, see what happens. Here's what I want to do. Let's see what happens when x gets to be a big number. Because here, it's saying when x is a big number, I end up with a small positive number. But this one says when x gets to be big, oh, you know what's even easier? Let's plug in when x is 0. Because look at, so this is how these work. Process elimination. What's the easiest thing to do? When this one, if x is 0, y is going to be some negative number. But if this one's true, when x is 0, y is a positive number. Well, that's pretty simple to check. What happens when I set x equal to 0? I get 7 over minus 9. That's obviously a negative number. Has to be this. Now once again, just so I don't mislead people, let me check my answers. I don't want to make a mistake and not realize till after the fact. So that looks correct. And that looks correct. Yep. All right, let's just do one or two more of these. Hopefully, once you understand, you realize that these maybe are not that difficult. All right, maybe this will be the last one. Starts out the same. Domain. I'm looking at the denominator. I need to factor this. X plus 7 times x minus 7. What can x not be equal to? 7 or negative 7. So the domain is going to be all real except 7 and negative 7. Looks like it's going to be A. Vertical asymptotes just springs from this, right? 7 and negative 7. Horizontal or oblique. All right, so let's look at our leading terms. And we notice here, top is larger than the bottom, and actually it's one larger. So you know what this is? This is going to be, let me do it up here where I have room. I'm going to have an oblique asymptote. So here I have to do my long division. Now, this is a good problem because I didn't do one like this before. So here it is. Let me start way up here. X cubed minus 3. Or was it 8? I marked through it and I can't even tell. I think it's, let me see if I can tell what it is. I'm going to assume It may not matter. I'm going to assume it's an 8. I don't think it's going to matter the way we're... Anyway, so in here, you notice I put x cubed, but here I don't have an x squared term or an x term. When I do long division, I have to include those. So what I'm going to do is x cubed plus 0x squared. So I've got my x squared here, but because I multiply by 0, the whole thing goes away, so it's not really there. But I need it to be there to do my long division. I don't have an x term, so I have 0 times x. And then finally, I'll end up, let me just assume this is a 8. I don't think it's going to matter. Now divided by x squared minus 49, x squared, I have to have my x term, so I put a 0x in here, minus 49. So here when you have some, you have to put these fillers in to do this long division. So now I say, what times x squared equals x cubed? Well, x does, right? So x times x squared is x cubed. X times 0x is 0. X squared minus 49x. I'm going to subtract this, so it's 0, 0, 49x, and I bring this down. I'm actually done with my division. So this whole thing equals x plus 49x minus 8 over x squared minus 49. Bottom line is this whole thing when x gets to be big, this whole thing basically goes to 0. So my oblique asymptote is y equals x. And now if I look at my graphs, vertical asymptotes, I have them all. Looks like they all have the correct oblique asymptote. So which one is correct? How can I determine? How about, let's see what happens when x gets to be, well, this is sort of, okay, this is one where I don't have my calculator with me. What I would do is, if this was actually, whoops, you can't see this, if this was on a test, you can see there are differences, like for instance, this graph, when x is negative, has this here. Here it's down here, here it's down here, up here. I would like plug in like negative 20 into this equation and see what the answer is. And therefore I would eliminate, well, I can sort of estimate. If I look at the end behavior, it's going to be x, and if it's negative, it's going to be negative. I believe it has to be either B or C, because this thing has to be negative. So then the difference is the middle part. So what happens when x is just a little less than 0, like minus 1? Well, minus 1 is negative 1 over 1. It's negative. I believe it should be C. Once again, this is just trial and error, sorting things out. So just out of interest, let me see if I'm actually correct. And it looks like I messed up. It should be B. But like I said, I don't have my calculator. So if I look closer, I could probably see where I messed up. But I think the rest of it is probably correct. Yeah, everything's correct except this last part. But I'm not going to worry about it because, like I said. Anyway, all right. Wow, this module had so much stuff in it. I guess 4 long videos, so hopefully this will help you understand what's going on. There's a lot of material in there, but hopefully this will help you.